Let us now see what are the power relations in a synchronous generator. Okay. So in a generator, whatever the kind of generator, the basic thing remains same. There will be a mechanical input which will give an electrical output. So if you take the mechanical input as P input and this as the P output, then what is the relation? The input power is equal to the output power plus the losses that are occurring in the machine. Okay. So we will see what is the power flow diagram for the synchronous generator. So we've already seen number of power flow diagrams for various machines, right? So this will also be more or less, it will remain almost same. First we will have the mechanical input, right? So the mechanical input P input is equal to the input torque into the angular rotation, the mechanical angular rotation of the rotor, right? Now we have to ensure that for the synchronous generator, the speed has to remain constant. Only then you will get a constant frequency. Otherwise the frequency will become variable at the output. So this is one important point you have to remember with respect to the synchronous machine. Okay. So then the first loss we can take to be the friction and windage losses. Right. Then next will be the core losses. Further we can take some stray losses as well. Okay. So what is the power that is now left out? This is the power that is left out. Okay. So this is what is going to be the power that will be converted from mechanical form to electrical form. Okay. But this is not the final output that is available at the terminals. There will be another loss here. What is that? The I square R losses or the copper losses. And finally, this power that you have, this is the output power that is available. Electrical output. Now the converted power we can express in terms of the induced torque, which is T induced into the angular rotation, mechanical angular rotation. Okay, where T induced is the induced torque. This is not equal to the input torque here, remember. Okay, input torque is different from the induced torque. Now this expression is in terms of the induced torque and the rotation, angular rotation. Now what about in terms of the voltage and current? If you take the equivalent circuit, this is EG, you're going to have resistance, inductance, this is the armature resistance RA, and synchronous reactance XS, and this will be the terminal voltage. So we are talking about the per phase equivalent circuit here, and we can represent the armature current as well. So now what will be the converted power? This will be equal to this voltage and this torque and into the cos of angle between them. Okay, so you can write P converted is equal to 3 times EG IA into cos of the angle between both of them. Okay, so you can write where gamma is the angle, or you can write phase, the phase difference between the generated voltage and armature current. Now what about the output power? P output is equal to 3 times the terminal voltage into armature current into power factor, right? 3 VT IA cos phi, where phi is angle between terminal voltage and armature current. This is in terms of the phase quantities, remember. If we are using the line quantities, then here root 3 will come instead of 3. Okay. Then what about reactive power? This is the real power output. Now the reactive power Q output, this is equal to what? 3 times Vt Ia sine phi. Now we will discuss the power flow equation. So you must have heard about power flow equation in power system stability, right? The electromagnetic power, this was equal to the voltage on one side of the bus into voltage on the other side of the bus divided by the transfer reactance into sine delta. Okay, so similar expression we are going to get here, because after all in a power system there is going to be a synchronous generator, and that is how we have got this equation as well. Okay, so first we will assume that resistance is negligible. Okay, so then only you are going to get this expression. So you can consider it to be sort of an approximated expression. Okay, so first we will draw the phasor diagram. This is the terminal voltage Vt. Now the power factor is phi, cos phi. Then at an angle of phi, you are going to have the armature current Ia. Now we know that the generated voltage is equal to, all in the phasor form, plus JIA XS. So what will be the, where will be the phasor IAXL? This will be 90 degrees leading to the current phasor. So you can extend this like this, and you can drop a perpendicular from this line. Okay, so now this is going to be the direction of the phasor IAXS, and what will be the magnitude? It will be equal to IAXS. So here we are going to have the generated voltage EG. Now what is the angle between EG and IA? This we have taken as gamma. Okay, now this angle between EG and VT, this is what we are going to take as delta. This is what we call as the torque angle. Now what was the real output power that was delivered? This is 3 times the terminal voltage into armature current into cos of the angle between them, which is cos phi. Okay, now if you construct a right angle triangle here. Okay, so this magnitude is IAXL. Now what is this angle? This is going to be 90 minus phi. In this triangle, this angle is going to be 90 minus phi. So this will be 90 minus phi. So this angle will be phi. Okay, then what about this length? This is going to be this length into cos phi, right? So this is going to be, you can write down IAXS cos phi. Okay, now in this triangle if you see, okay, this length of the hypotenuse is EG and this angle here is delta. So what will be the length of this? This will be EG sine delta. Okay, so this length is also equal to EG sine delta. Okay, so from here IAXS cos phi is equal to EG sine delta. Okay, so you can write IA cos phi as EG by XS sine delta. So this is the expression that you will substitute in this equation. Okay, so instead of IA cos phi, you're going to write EG sine delta by XS. So then what are you going to get? This implies the output power is equal to 3 times Vt EG by XS into sine delta. Okay, so you can see here this is in the same format as what we have discussed in power system stability. Okay, now this 3 here, what is it? It means it is for all the 3 phases. So this is the important final expression for the output power, but remember we are assuming negligible armature resistance. Now the induced torque also you can express as the P converted divided by omega m, right? Now since we are assuming negligible resistance, armature resistance, there will be no copper losses. In that case, the converted power is simply equal to the output power, right? So you can write down this is equal to P output divided by omega m. You can write down the reason also, because RA is negligible, the copper losses will be 0. So the converted power is simply equal to the output power. Okay. So then you can write as P output is nothing but 3 Vt Eg by Xs sine delta. So you can add one more term here, omega m. Okay. So when the resistance is negligible, then you will get two simple expressions for the output power and the induced torque. Now what if we do not assume the resistance to be negligible? In that case, how do you find out the expression for output power? So it will be a little bit lengthy, but we will see the procedure still. Okay. So this is Eg. We have armature resistance, the synchronous reactance Xs, and the terminal voltage. So we will take terminal voltage to be the reference phasor. So that means it is going to be Vt angle 0 degrees. Okay. And the generated voltage we can take to be at an angle delta with respect to the terminal voltage, right? Because delta is the angle that we take between terminal voltage and the generated voltage. Okay. So we can write down the expression for armature current. This will be equal to Eg angle delta minus Vt angle 0 degrees divided by Ra plus Jxs. Okay. So now you're going to get some magnitude and some angle, right? Now once you find that out, then the complex power, the total output complex power, this is going to be 3 times Vt into Ia conjugate. We're talking about the phasors here. Okay. So we know Vt, magnitude Vt and angle 0, and Ia we find out the magnitude and phase from this expression. Then you write the conjugate of it. Okay. So now whatever real and imaginary part that you're going to get, from there you're going to get the real power and imaginary or the reactive power. Okay. So P output and Q output. This is the procedure if you are not neglecting the armature resistance.